We'll continue to talk about the aftermath of inflation, in particular the origin of matter energy and the structure of the universe. Besides the flatness horizon problems, another issue was the standard Freeman and Roberts Walker cosmology that it requires an initial conditions that all the energy in the matter of the universe be present at the very beginning. Furthermore, this hot plasma of particles and radiation should have just the right amount of initial density and homogeneity, or what we call density perturbation, to form through subsequent gravitation clumping the cosmic structure of galaxies, cluster galaxies, the voids, etc., that we observe today. Remarkable that the inflation cosmology can explain the origin of matter and energy as well as the structure of the universe. In fact, many would argue that while it's impressive that inflation can solve the horizon and flatness problem, its greatest success is furnishing the mechanism for particle production and for seeding the inhomogeneity required for the subsequent formation of cosmic structures. In this inflationary scenario, all the matter and energy could have been created virtually from nothing. Furthermore, the phenomena of particle creation in an expanding universe can be qualitatively understood in terms of semi-classical potential energy picture. Particles were created when the system fell into and oscillate around the true vacuums. You start from false vacuum, and this oscillation in quantum field theory is corresponds to production of particles. Particle creation may be understood more directly in terms of quantum fluctuations of a field system. These fluctuations can take the form of appearance and disappearance of particles, antiparticle pair in a vacuum. Such energy non-conserving processes are permitted as long as they take place in sufficient short time delta t so that the uncertainty relation delta E delta t less than the Planck constant is not violated, which we talked about already in the quantum fluctuation when talking about Hawking radiations. In expanding space, in this case here, in contrast to static situation, uh, real particle can be created. Remember, for the static case, this cannot take the long time scales. It's just like Hawking radiation, the present event horizons. Okay, it's just in the black hole you have the event horizon. In here we have expanding uh, space, especially exponentially expanding space. Thus, inflation in conjunction with quantum field theory naturally gives rise to particle production. This hot, dense, uniform collection of particles is just the postulated initial state of a standard Big Bang model. View the inflation as so the universe views inflation as the ultimate free lunch. Uh, we see that inflation theory, the matter energy originated from the false vacuum, which is through a phase transition, as the scale factor A was inflated, say by a factor 30 orders of magnitude. The matter energy increased by because A to the cubed 10 to the 90. But energy conservation still holds because this increase in positive matter energy was just balanced by the negative gravitational energy. The fact that gravitation is negative is also true in GR, just like in Newtonian theory. The total energy, matter plus gravitational, remain constant and very small. It could even be exactly zero. Remember, we talked about the flat universe, the, the signature, the Courage signature is directly related to total energy and energy balance equation. Conservation of energy places no limit on how much the universe can inflate, as there is no limit to the amount of negative energy it can store in the gravitational field. Here I quote Alan Guth himself. This borrowing of energy from the gravitational field gives the inflationary paradigm an entirely different perspective from the classical Big Bang theory, in which all the particles in the universe, at least their precursors, were assumed to be in place from the very beginning. Inflation provides a mechanism by which the entire universe can develop from just a few ounces of primordial matter. Inflation is radically at odds with the old dictum of Democritus and the Lucretius. Nothing can be created from nothing. Well, if inflation is right, everything can be created from nothing, or at least from very little. If inflation is right, the universe can be properly be called the ultimate free lunch. So we talk about quantum fluctuation and the seeding of the cosmic structure. Furthermore, inflation could stretch subatomic size fluctuations of quantum field into astrophysical size density perturbations to see the subsequent formation of cosmic structure. The result density fluctuation will be Gaussian, means it's a maximum random, and scale invariant. That is the same fluctuation in all length scales, same fluctuation, of the order of 1 part in 100,000. In agreement with the observed CMB and anisotropy power spectrum and large-scale galaxy surveys. Okay, so this are supported by observations. Now we'll talk about inflation and the primordial gravitational waves. Inflationary expansion would necessarily have created big ripples in space and time, which is gravitational wave. The detection of such primordial gravitational wave would constitute a definitive evidence for cosmic inflation. Such gravitational wave would have impacted all the matter in the universe. In particular, the spin-tuned tensor nature of such perturbation would have led to anisotropy of the plasma and its coupled radiation at the recombination time. Okay. This anisotropic radiation would have become polarized by scattering of electrons, which we talked about in a little more detail in box 10.3. From the presence of such things called B-mode polarization pattern, we can in principle deduce the existence of the quadruple anisotropy imprinted by and only by primordial gravitational wave on the plasma just before photon decoupled. These CMB signals are expected to be very weak. They came as a great surprise in the spring of 2014 that BICEP collaboration announced the discovery of B-mode polarization in CMB. Upon further joint analysis with the European Space Agency Planck Group, it became clear that the initial signal can be accounted for by contamination from the foreground dust of our own galaxy. Nevertheless, with several collaborations having ever more powerful instruments pursuing the study, it is hoped that with more sensitive analysis, the primordial gravitational wave signal could be discovered in not so distant future. Here's the polarization pattern of B mode and the BICEP 2 claim to have discovered. Finally, we could talk about eternal inflation and the multiverse. Our current level of physics understanding the inflation cosmology is a framework, not a real theory yet, in a sense with all the details. It postulates the existence of a quantum inflaton field that momentarily transitions to a state having a large cosmological constant. In the specific spontaneous symmetry breakings example we talked about, the false vacuum brought about the exponential expansion of the space. In the semi-classical description, the system then rolled down the potential energy curve slow enough that can convert its potential energy into particles kinetic energy, and was followed by the initial decelerating expansion of the Freeman, Lemaître, Robinson-Walker universe. From a broader perspective, one can regard this false vacuum as just a quantum state subject to quantum fluctuation and the slow rollover process as a quantum decay. From this point of view, such transition was random process, and such a phase transition can happen at any place in the cosmos and last forever, hence called eternal inflation. This suggests a wider view of the cosmos as a large collection of widely separate regions, each the aftermath of a portion of space that underwent inflationary explosion. We might picture such a collection as a multiverse, a huge cauldron of chaotic eternal inflation, with causally disconnected parallel universes perpetually bubbling into existence. So, the lesson from lecture 28. The theory of cosmic origin posits that in its earliest moment, the universe underwent a huge expansion due to the phase transition into field state with a large vacuum energy. This scenario solves the two serious issues regarding the initial conditions of the standard Freeman-Robinson-Walker cosmology, the flatness and the horizon problems. This primordial inflation answers Hoy's Big Bang objection by explaining not only the origin of all matter energy in the universe, but also the unevenness in its initial distribution that led to the subsequent formation of observed cosmic structure. Inflation cosmology implies a flat spatial geometry, which is verified, and a primordial gravitational wave, which is yet to be observed for certain. In the next lecture, we're going to talk about the large cosmological constant inflation cosmology brought about the explosion that was the Big Bang. Next, we're going to talk about the effect of another much smaller cosmological constant in the form of so-called dark energy, which is the most important part of the energy budget of the universe now. This dark energy causes the expansion of the universe to accelerate. The accelerating universe was discovered observationally in 1996. In the theory front, we still have so-called the cosmological constant problem, okay, which we're going to talk next time.